Hello, this is David Scher. I'm back again with another lecture in Physics 578, Medical Health Physics. Our spring break begins next week, so I'm squeezing in a lecture here on patient release criteria in nuclear medicine. And I'm going to share my screen and begin that right away. So one of the things that health physicists are involved with in many hospitals is establishing criteria for when a patient can be released that have radioactive materials in them. And so this is one of the things that we need to do well, and so I'm going to cover this today, hopefully as clearly as possible. So the reason this is an issue is that the regulations require that when a person has radioactive material in their body, either in unsealed form or as an implant, then the patient may be released from radioactive controls or radiation safety controls if the effective dose equivalent to members of the public is not likely to exceed 500 millirem or 5 millisieverts. If the effective dose equivalent is likely to exceed 1 millisievert, 100 millirems, then there must be instructions provided to the patient about reducing the dose to others. And we will discuss that. If the patient is nursing an infant or is likely to nurse an infant, and the dose to the infant from breastfeeding could exceed 1 millisievert, then there needs to be instructions to the patient and information to the patient about the consequences of failure to interrupt breastfeeding. And in the case of any of these requirements, then when we determine the basis for releasing the patient, there needs to be a record maintained of that, subject to inspection. And the same is true for instructions to nursing mothers. The records of that must be maintained. The NRC has published Reg Guide 8.39, a relatively recent revision in Revision 1, and this provides an acceptable approach. Now, I would point out that the rules that I just read apply to all patients with radionuclides. It doesn't matter whether it's radiation therapy with a permanent implant and they're going home, whether it's radiopharmaceuticals. Nothing in the rules says anything about therapy, so it includes diagnostic procedures as well as therapeutic procedures. Now, most diagnostic procedures involve a low enough dose that it's not a concern, but it's still, there's nothing in the rules that specifies this is only for therapy and only for unsealed nuclides. It's everything. Now, the reg guide that I'm talking about has 5 methods for demonstrating compliance, that establishing release criteria when it's acceptable to release a patient from radiation controls, with 5 different sets of assumptions. I'm going to go through that in this lecture. Now, I will point out, as the NRC does all the time, that reg guides are merely guidance, that licensees are allowed to depart from the assumptions in the reg guide if they use patient-specific data, but they must record the basis for their decision, all the calculations and the data that they used in coming to their decision, and that's subject to inspection by the NRC and second guessing, of course. Now, the basic approach that's used for releasing patients from controls is that you need to calculate the dose to an individual, or just the dose at 1 meter from the patient. So the assumption is that personnel, members of the public, will be at a distance of 1 meter from the individual. In addition, there are occupancy factors. How long will an individual stay within at a distance of 1 meter? And guidance that's in the reg guide is that if the physical half-life of the nuclide is less than 1 day, you assume that the person is there the whole day. The occupancy factor is 1 for nuclides with a half-life of less than a day. The occupancy factor can be reduced if the physical half-life is greater than a day, and if patients can comply with lifestyle instructions that will maintain exposures low. Another basic part of this approach is that ingested or inhaled radioactive materials from the patient to other members of the public, it's based on the assumption that 1 part in 10 to the 5th would be transferred from the patient to other people. There's a common rule of thumb that's been supported by some anecdotal evidence that about 1 part per million, 1 part in 10 to the 6th, is transferred in working conditions. And so the NRC adopts a factor that's 10 times greater than that for conservatism. However, the rules or the guidance says that if the dose that is due to internal doses is less than 10% of the regulatory standard, then we don't have to include it in our records or in our consideration. Okay, the basic approach is that the dose rate for the patient is modeled as a point source. So the dose rate at some time t is the initial dose rate divided by the distance squared times e to the minus lambda t. This e to the minus lambda t takes account of radioactive decay. The r squared takes care of the inverse squared law, and d0 is the empirical, the dose rate being emitted initially. Now, d0 can be measured and just evaluated based on that measurement, or we can use the specific gamma ray constant. The gamma ray constant is a factor that tells us what the dose rate will be per millicurie or per curie or per unit of activity at a specified distance. Ones that are provided in the NRC Reg Guide are rem per hour per millicurie at, I believe, a meter. The cumulative dose rate, then we take this dose rate, that's the dose per unit time. We integrate it. The cumulative dose during a period of t, from 0 to t, is the integral of the dose rate. If we do this integral with this equation, we get this result. It's not it's a very common result. We've seen it before in other applications, but when we do the integral of an exponential, we get the factor in the exponent brought down to the denominator, and 1 minus the e to the minus lambda t. So in the Reg Guide, they make reference to half-lives rather than decay parameters. The connection between the decay parameter and half-life is shown here. And so another factor that's necessary is the gamma factors that are provided in the Reg Guide are rem per hour, and the half-lives that are listed in the Reg Guide are in days. So we need to convert so that we use consistent standards. We have a dose rate is the time, and so they have to have the same time units to be consistent. And so if we make that conversion from this equation, then 1.443 is the inverse of the log of 2. It's 1 over 0.693, 24 hours per day. The initial dose rate, this is the physical half-life, is 1 over lambda, and the r squared. And this is the decay constant for however long we've gone. So if we combine these factors, it's the 1.443 times 24, we get 36.4. So if we consider the dose that's administered over a period to the end of time, all the dose administered by to a member of the public, the d infinity, it's just these factors. So 36.4 times the initial dose rate times the physical half-life divided by the distance squared. That's, I think, a fairly straightforward equation given what we've gone through in our training at Illinois Tech. Now the reg guide gives us 5 methods, 5 sets of assumptions that we can use. First method is based on the administered activity and the physical half-life. The second method is based on the measured exposure rate and the physical half-life. Then we'll look at activity and measured exposure rate and the effective half-life. And the third is a 3-compartment model used for iodine 131. We'll get to that near the end of the lecture. So the first method is based on administered activity and decay. So in our equation for D infinity, the initial dose rate is the administered activity times the gamma factor. That gives us the dose rate that's initially present, given whatever activity it is. In this model, we're assuming that elimination is solely based on radioactive decay, the physical half-life. There's no biological elimination. So the physical half-life is what's present in this equation. We have occupancy factors E, and we'll go into this in some detail later, but the occupancy factor for a half-life that's less than a day is 1. Occupancy factor for periods that are longer than half-lives of longer than a day are a quarter. They assume a person's present and absent over the longer period, less. And if someone lives alone, the occupancy factor can be 1/8, 0.125. One of the assumptions involved in all this is that there's no shielding by the patient's tissues. Nothing in what we did earlier when we derived this equation had anything to do with attenuation due to the patient. So that's one of the conservative assumptions. So what we do to come up with a release criteria is we know a particular what isotope we're dealing with. We put that in for gamma. We know what the physical half-life of that isotope is. We put it in for TP. We choose our occupancy factor, put that in the case, in the equation. We know our distance is 100 centimeters, and set the total dose overall time to half a sievert. And then we calculate this and use this to determine what Q0, what the initial activity would be that would result in a 500 millirem dose to a member of the public. The next method is very similar, but instead of using the activity and the gamma factor, we just simply take our measured dose rate. We measure a person's dose at 1 meter at the time we want to release them, and then we assume that they're going to decay through physical decay only, not through biological elimination. And then the model will be based on this is method 1. Method 2, the model will be based on our measured activity and the physical half-life. And 36.4 is due to that 24 hours a day, and the 1.44 from the logarithm of 2. So we put in the correct occupancy factor based on the half-life and the person we're dealing with, their ability to live independently. And one thing I'll notice is that because we're using a measured dose rate from a particular patient, this implicitly includes the shielding the patient provides. It will be less than what we would calculate if we use the attenuation, the gamma ray factor times the activity that's present. Again, same game. We set this total dose overall time to 500 millirem or half a sievert. Figure out what the D0 prime, what the dose rate would be that would result in that total dose, and that's when we can release the patient when they reach that dose rate. So in Reg Guide 8.39, they provide a table showing us when we can release patients that would, using this model, would result in a dose of 500 millirem at 1 meter from the patient. So they give it both in terms of activity, which is our model 1, and the dose rate measured from the patient, which is our model 2. And for any given isotope, we can find out at what point we can release the patient. Now, why would you use the activity for this calculation instead of measuring the activity, the dose rate, since the dose rate includes the shielding, etc.? Well, implicitly? Well, the reason is that we want to be able to predict this. We want to know when we'll be able to send the patient home, and we know what activity we're going to administer. We have not yet measured the patient, so we don't know what their dose rate is when we're doing the planning. If the patient could deliver over 100 milligram to a member of the public, instructions are required. The assumptions here with regard to occupancy assume that the patient is able to comply with those instructions. So the clinician, the authorized user, the nuclear medicine physician needs to make a determination as to whether the patient is able to comply. If the patient is highly dependent and can't care for themselves and is immobile, then there may be questions as to whether the patient can comply, and so they may stay in the hospital longer until they eliminate more of the radioactive material from their body. But if they activity will result, the activity that are administered and the dose rate they have would result in a dose of less than 100 milligram at a meter to a member of the public, they can be discharged without regard to instructions, and those considerations don't come into play. And so there is a table also in the reg guide that, with the same kind of calculations, tells us at what activity or what initial dose rate a person would not deliver 100 milligram to a member of the public, and so they can be released without the instructions or the ability to follow the instructions. Okay, so that's also useful for us for planning purposes. Notice that diagnostic doses, imaging doses, almost always fall under this criteria. We don't need to provide release instructions to patients who undergo diagnostic procedures. For example, it's 150 millicuries of technetium-99m. That's 5 to 10 times the dose is given for diagnostic procedures. And so you can see this is why we don't, in practice, we don't need to worry about this concern for diagnostic procedures. The third method takes into account the administered activity and then allows us to consider biological clearance. So the difference from method one is in method one, we use the physical half-life, T sub P, and now we're going to use the effective half-life, T sub E. We have to use, if we're going to use this method, we need to use effective half-lives that are based on patient-specific measurements. The elimination rate that the individual exhibits. This is often done for some procedures, that this is measured as part of the workup to determine what dose to administer to the patient. The physician needs to know how long that material will be resident in the patient's body to know what dose will be delivered and be effective. And so this data is often available for some kinds of procedures. Now, notice that when we measure an effective half-life, we're measuring the time rate of change that includes both the physical half-life, physical decay, and also includes the biological elimination. So what we're measuring is the effective half-life. However, just for clarity, the relationship between the biological clearance half-life and the physical decay half-life and the effective half-life is shown here in the third bullet point. Okay, there are no tables in the reg guide for this method because it's based on patient-specific data, and so you need to use the formulas. The fifth bullet, we have the equation that involves the effective half-life, TE, and the administered activity and the gamma dose rate constant. And so to know what the clearance, when the person can be released, we set the dose overall time to 500 millirem, and we set the distance to 100 centimeters. We choose an appropriate value of the occupancy factor. We have the measured half-life, and we know the initial activity. And then we can determine at what initial activity the patient can be released. And when you do calculations, that use patient-specific release criteria, then records must be maintained of the basis upon which how you came to the conclusion of the factors and how this calculation was performed. The fourth method is based on a measured dose rate from the person and the biological clearance rate, very similar to the last one, only instead of calculating the dose rate based on activity, we measure the dose rate from the patient at a meter. We, again, set D infinity equal to 0, to 500 milligram, half a sievert. We calculate, we know what the TE is, we know at what dose rate they can be released then, and that's how we make our decisions. There's a fifth approach. It's an iodine-specific model. It includes a 3-component model or a 3-compartment model. And the 3-compartment, its model is based on an administered activity, Q0 at time equals 0. Model assumes there's circulation throughout the body for 8 hours, and during that 8-hour time, the only way activity is eliminated is via radioactive decay. So at the end of 8 hours, that all at once, 80% of the initial activity is eliminated. And throughout that period, 80% of the activity is undergoes radioactive decay. Then there are 2 compartments after that 8 hours are completed. There's an extrathyroidal fraction, F1, that has an effective half-life, T1E, and a fraction that's in the thyroid, F2, with an effective half-life of T2E. And so there's an occupancy factor, E1, that applies during the first 8 hours. So someone will be present or not present with that person during the first 8 hours. And then for the other portions, they have another occupancy factor for later times. Just like we had an occupancy factor that applies for short-lived materials and longer-lived materials. The uptake fraction and the clearance times, these F1s and F2s and TEs, are based on the patient's condition, what the reason they're being treated. Okay, and then I'll show you a slide with that in just a moment. So here's the equation that we use. This first term, 36.4 gamma Q0, that's the dose rate at 1 meter from the material when it's first ingested. And so we have an occupancy factor for the first period, and it's only by physical decay. 80% of it is in this compartment. And so over the course of that time, it decreases by this amount. This is for the period of 8 hours. That's why it's 0.33 days. And so dose is delivered to a member of the public during that time. Then there's another time subsequent to that. So the material underwent decay during the first 8 hours, and then it was taken up into the thyroid. So this decay constant in these, or it goes to body parts that are not the thyroid. That's what the E2 is, extrathyroidal. E2 is the thyroid. So F1, E2 is the occupancy factor during after the first 8 hours. So F1 is the non-thyroidal fraction that goes to other tissues other than the thyroid. It has a certain effective half-life. And this component is the material that goes into the thyroid. It decayed while it was circulating for the first 8 hours. Then it is taken up with fraction 2, and it lives there for the lifetime in the thyroid. So here are the different parameters that are used in this model. If the person has hyperthyroidism, we assume that 10% stays in tissues other than, 80% is washed out in the first 8 hours, at the end of the first 8 hours. Of the part that remains, 20% is in extrathyroidal tissue, 80% is in thyroidal tissue. Now, for a typical euthyroid healthy person, uptake fractions are between 0.3 and 0.5. So this person is hypothyroid. They're metabolizing a lot of the iodine into their thyroid. 80% of it goes there. 20% remains in the rest of the body. The elimination time, the effective half-life, is 0.32 days, so about 8 hours. In the non-thyroidal compartment and 5.2 days in the thyroid. Some patients undergo cancer treatment, so they will have had their thyroid, the gross or gland will have been removed, and there may be cells either in the thyroid bed or as metastases throughout the body. The uptake fraction is very small. They model it as 5%. 95% is present in the rest of the body, 5% in the taken up by the thyroid tissue. Again, the part that's not in the thyroid has an 8-hour half-life. The part that's in the thyroid tissue has a 7.3-day half-life. Now, this person has had their thyroid removed. All they have are small cells distributed throughout the body. 5% is a very conservative assumption. It's not uncommon to have an uptake of 1% in these patients. So these graphs on the right show the elimination rate of different conditions. The blue graph shows what life looks like, what the elimination rate is based solely on radioactive decay. So that's what the model 1 is, if we assume there's only radioactive decay. The red line in this graph, the next one down from the top, is based on a euthyroid, a person with a normal thyroid, and the effective half-life instead of the just depending entirely on the radioactive decay. You can see that there's much less activity. There is less activity compared to just the physical decay. The third slide, the light green, it shows what the elimination rate is from hyperthyroidism. So 80% of the activity remains in the body, is locked in the thyroid and decays away very slowly. The last graph, purple graph, bottom line, shows what a typical clearance rate would be for a post-surgical patient undergoing radiation therapy. And so there's most of the activity is eliminated from the body quickly. The part that's retained in the random cells lasts for a longer period of time. And so that's what this graph shows. Occupancy factors. So let's go into details about the occupancy factors that are selected. The table 1 and table 2 we saw are based on the most conservative assumption that someone's present at 1 meter the whole time. The occupancy factor is 1. If you use an occupancy factor other than 1, you must record in your record of the release criteria. 0.75 is possible when the physical half-life, the elimination rate from the person is less than a day. You can use up to a 0.75. If there's evidence the person will, this makes sense given the person, their ability to take care of themselves independently. 0.25 can be used when the effective half-life is greater than a day, and the patient can comply with the following instructions. They'll maintain a distance from others for at least 2 days. They'll sleep alone for at least the first night. They won't travel by airplane or public transportation. Again, they'd be close to members of the public in that case. And won't go on long automobile trips for the first 2 days with any other people. So if a person needs a ride home, for example, and they can't drive themselves home, then the use of 0.25 would not be appropriate for that patient. They have to. This would be appropriate. The occupancy factor of 1/4 would be appropriate if they have a bathroom that they can use and others not use for the first 2 days, and that they would drink plenty of fluids to eliminate the materials within the first 2 days. Occupancy factor of 1/8 is also permissible if the half-life is greater than a day, if they follow all those instructions and they live alone for at least the first 2 days, and they agree to have few visits by family or friends during those first 2 days. And so that's how we select the occupancy factors that are appropriate. Another part of the regulations deals with breastfeeding. the 10 CFR 35.79 specifically addresses breastfeeding, and we must provide, if the dose to a breastfeeding infant will be greater than 100 milligram, we need to provide instructions to the patient and describe the consequences if those instructions aren't followed. So that in the reg guide, there's a table 3, I believe it is, table 3, that tells us what the activity would be that would require assumptions based on the kinetic modeling we've already described. Then column 2 tells what the activity above which a record of these instructions is required. So column 1 is the activity that would not deliver 100 milligram to an infant. Column 2 would has a potential to deliver 500 milligram, and so a record of the instructions is required when it's potential to deliver 500 milligram. Column 3, so the advice we would give, this is a typical advice that NRC recommends in the Reg Guide, based on what agent they've been administered with, how long they should suspend breastfeeding. And so in many cases with technetium 99M, has a short half-life, 6 hours, they just recommend suspending breastfeeding for 24 hours. And for iodine 131, they recommend complete cessation of breastfeeding for the child. These are other agents. This table is available in Reg Guide 8.39. This is provides the basis for our recommendations with breastfeeding. Now, I mentioned before that internal doses to the members of the public, other than breastfeeding, are based on the assumption that 10 parts per million of the activity is transferred to members of the public. This is a very conservative assumption. Most of this activity is locked in the body or eliminated in urine or feces, and so it's unlikely that someone would pick up this much activity. As I said, in occupational situations, when people work with a certain amount of material, a typical number is 1 part in a million, not 10 parts in a million. So calculation of this is based on using the dose coefficients from Federal Guidance Report 11 I showed you before, the dose coefficients to convert from activity to dose. We use the stochastic dose coefficients because that's what we're concerned about with members of the public. If we do the calculation and it turns out the dose would be less than 50 milligram, 10% of the standard, it doesn't need to be included in our decision making. Now, I did do a brief example here for iodine 131. Now, this applies to all the isotopes. These requirements, just iodine. Iodine is a very common isotope, but there are many others being used as well at high activity. But for iodine 131, if we have an initial activity of 200 millicuries, that's high but not out of this world kind of dose for a post-surgical thyroid ablation. Then the internal dose due to this 200 millicuries times the dose coefficient, 53.3 rem per millicurie, would give 100 millirem. In this case, this is more than 10% of the standard and would have to be included in our calculation. Now, I will point out that this whole topic related to release criteria is fairly controversial. Many practitioners argue that the methodology is excessively conservative, that this is places a burden on patients because of the requirement to stay in the hospital for non-medical reasons, only for radiation safety reasons, adds an expense. Also, a psychological factor of being away from home. So people are not required to follow 8.39. They can develop their own assumptions and methods. But 8.39 is a safe harbor, so many institutions decide to follow 8.39, knowing that they'll be protected from regulatory issues. as I said, the rule is about likely doses to members of the public, doses that are likely to be that no one is likely to receive more than 500 millirem from the radiation emitted by this person. So other defensible assumptions may be accepted by the NRC, etc. So that's what I have for you today. I thank you for your attention. When we come back from spring break, you have a week off. I'm not going to give you a homework assignment today, but I believe I'm going to give you a homework assignment working out some examples of release criteria and ask you to determine whether a patient would be released or when a patient could be released. So thank you very much for your attention. I hope you have a great break, and then we'll come back and work more on nuclear medicine.